Hi everyone. In this video, I'm going to discuss uh, some of the fundamental elements of the fundamentals of fluid flow, such as the types of flow, forms of energy, Bernoulli's energy theorem, grade lines, energy equations with machines and considering losses, and other important properties of the grade lines, and some important elements and formulas. So let's define a path line. A path line is the path followed by a particle. So if these are the path lines for a certain particle, it follows a certain path, and that's called a path line. Stream tube is a small bundle of path lines, such as this. So we call that stream tube. Laminar flow is a type of flow where paths of individual particles are parallel to each other and they do not cross. So, like this one, the paths are parallel to each other. Opposite to laminar flow is the what we call turbulent flow, in which paths of individual particles form a very complicated network. So, if the particle is at the center at one instant, then in another instant it may be at the top, bottom, and so on and so forth, that paths continuously form a very complicated network and they cross. However, most engineering types of flow belong to the turbulent flow. Now, there are conditions for which laminar flow can be expected, although this is very rare. One is high viscosity. If the viscosity is very high, then we expect that the flow is laminar because resistance to flow will be very, very high. Second is low velocity. Because of high resistance to flow, as a result, the velocity will be low. So we expect laminar flow, such as flow through voids through soil, where a, a water particle may travel only 1 centimeter in a year, depending on the type of soil. So we expect laminar flow for that. Another thing is the drag in a syringe. Then if you do not push the syringe, then the drag will not flow. So we expect very low velocity. Why do we expect a very low velocity? Because of the third condition, that the cross-sectional area is very small, or small cross-sectional area. That also uh, is the result of this laminar flow. What is the meaning of the symbol Q? Q has a unit cubic meter per second. We call it discharge, or volume flow rate, or simply flow rate. So that's the term for the symbol Q, where Q is equal to area times V, small v, and V in other situations, V is replaced by small u, where A is the cross-sectional area in square meter, and V is the mean velocity or average velocity of flow in meters per second in SI units. Types of flow. One is the uniform flow, where when the mean velocity at any section of the stream is constant. So the term uniform flow must be associated with constant mean velocity at any section of the stream. Then we have, this implies constant cross-sectional area for the velocity, for the mean velocity of flow to be constant. Steady flow, when the discharge at any section within the reach of a stream is constant. So that means the volume flow rate or the discharge is constant. Then in differential form, Q is the derivative of volume with respect to time, and it should be constant. So for steady flow, the associated term for it to recall is constant discharge. Then lastly, we have continuous flow when the number of particles passing a section of the stream is constant. Since we cannot count the number of particles of a flowing fluid or liquid, then this implies constant density or constant density in general. So that means for continuity equation for liquids, because liquids are considerably incompressible compared to gases. So liquids are in general incompressible when the pressure that will develop normally is in kilopascals. It seldom reaches megapascals unless for LPG gases. But most flow in engineering, the pressure will only be in kilopascals level. So that's why the liquids are considered incompressible. So the continuity equation for liquids would just be Q is constant. That is, Q equals Q1 equals Q2 discharged at any other section. Even if the cross-sectional area changes, the discharge must be constant. That's the continuity equation for incompressible liquids. Liquids are in general incompressible. Since Q is area times mean velocity, then it should also be equal to area 1 V1 equals area 2 V2 equals that area n Vn. Then let's have the term mass flow rate in kilogram per second. Mass flow rate is the product of discharge and density. So cubic meter per second times kilogram per cubic meter will give us mass flow rate. Or since Q is area times mean velocity, so it is also area mean velocity times density. Then the weight flow rate is in newtons per second or kilonewtons per second. It is defined by the product of Q and discharge and specific weight or unit weight of fluid. And it is in newtons per second. Then you may replace Q by area times mean velocity. So that's the expression for weight flow rate. Then continuity equations for compressible fluids, especially gases. So it is either mass flow rate constant or weight flow rate constant. That is Q rho equals Q1 rho 1 equals Q2 rho 2 equals Qn density n. Or Q times gamma equals Q1 gamma 1 equals Q2 gamma 2 equals Q sub n gamma sub n. Then let's proceed to the forms of energy in fluid mechanics. One is the elevation energy or elevation head. This is manifested in a fluid by virtue of the height of the fluid above some arbitrary datum. So the datum line is arbitrary. You can select it. You can move it. If you want, you have the control of the datum line. So it is equal to weight times Z or mgz, just like potential energy in physics. So W times Z. However, in fluid mechanics, W is taken as 1 Newton. So therefore, it results to just Z. The original unit of elevation head is supposedly Newton meter per Newton of fluid flowing. So that's why the unit reduces to Z. In meters, energy should be in Newton meter. But because the weight is taken per 1 Newton, then it results to just meter. Remember, the original unit is Newton meter per Newton. Next is pressure head or pressure energy, or the flow energy manifested in a fluid by virtue of the pressure transmitted by the surrounding particles to the other particles. So this is defined by pressure over specific weight. And that should also be in meter. Next is the velocity head, or manifested in a by fluid particle by virtue of the particle's velocity, of course. So it is 1/2 mv square originally. Since mass is weight over g and weight is 1 newton, therefore it reduces to v square over 2g. So that's the velocity head. So the total energy in a system without a machine therefore is E, and it consists of velocity head, pressure head, and the elevation head. And that should be in Newton meter per Newton, which results to unit of meter only. So if this is the pipe or stream, then we have a point here and we have an arbitrary datum. For instance, the total energy with respect to this arbitrary datum consists of these three forms of energy. So we have velocity, then this particle flows because of pressure also. Then those are the forms of three forms of energy. If those forms are available. Then power denoted by P, units will be in watts, foot-pound per second in English system. Kilowatts, 1 kilowatt is 1000 watts, or in horsepower. So power is weight flow rate times the energy. So if you check the unit, if Q is in cubic meter per second, gamma in newtons per cubic meter, and in energy in meter, that would give us Newton meter per second or watts. If you want to make it in kilonewtons, then specific weight must be in kilonewtons per cubic meter also. So horsepower is Q gamma E over 746 if Q gamma E power there is in watts, because 1 watt or 1 horsepower is 746 watts or 550 foot-pound per second. So that's the conversion factor. So we then proceed to the Bernoulli's energy theorem, which states that neglecting friction, the total energy at any section of a stream is constant. That is, the energy grade line, or the energy at one point is equal to the energy at any other points along the path of a stream. So for instance, this is a pipe and we have imaginary piezometers here, and this is the selected datum, arbitrary datum. Remember, this is arbitrary. Call that point 1 at the center of the section of that pipe, point 2 at another section. This will be the energy grade line, which is horizontal if friction is negligible or neglected. So these are the forms of energy. We have Z1 here. Because of pressure, the liquid will have to rise to the what we call this level here, wherein it is imagined to be in exposure to the atmosphere. So it will rise because of pressure. That distance from 1 to that liquid level is the pressure head. So this is elevation head, pressure head at 1. And because there is velocity at 1, then this is the velocity head v1 squared over 2g. Then at point 2, we have z2. Because of pressure, the liquid will rise there. So this is z sub 2. Then we have pressure at 2, pressure head at 2, then velocity head at point 2. So notice that the pressure at the bigger section is higher than that at the smaller section. So most of you may be thinking that the pressure at the smaller section is higher. Just remember that bigger body, when you place it over a small body, the pressure will definitely be great. Whereas when a big body is, when the small body is put over the big body, then it's like nothing happens. So that's the wrong idea that the pressure is high at smaller section. it is at the bigger section. What is high at the smaller section? It is the velocity. So if the section is smaller, you notice that in anosol, the velocity is high. That's why the velocity head is high, but the pressure is low. In one section, the pressure head is high, but the velocity head is low. So that's why energy at section 1 equals energy at section 2. So there's no head loss because friction is negligible. So the equation would be, that's the energy grade line, and this is called hydraulic grade line. The hydraulic grade line is a line joining liquid surfaces in a series of piezometers. So if you imagine so many piezometers, you just connect those liquid surfaces in the piezometers. So this is the equation by this theorem here. So the total energy at section 1 is equal to the total energy at section 2, and so on and so forth. So that's why this vertical total energy is equal to the vertical total energy there. But this is the energy equation considering head loss. This is the real system without a machine first. So the energy grade line will fall, will slope downward because of the head loss. So same arbitrary datum, same points. So we have elevation head at 1, pressure head, and this is velocity head at 1, that's energy grade line, hydraulic grade line, velocity head at 1, and at 2 we have elevation head, pressure head because of pressure at point 2, and velocity head which is still high at point 2. Then the drop in the energy grade line, the distance between the energy at point 1 to the energy at point 2, the drop is called the head loss, denoted by HL, capital HL. So the energy equation would become velocity head at 1 plus pressure head at 1 plus elevation head at 1 equals velocity head at 2, pressure head at 2, elevation head at 2 plus the head loss, so that they are equal. So that's the energy equation at section 2. So power loss, therefore, considering head loss, would be weight flow rate times the head loss. So it may be expressed in watts or kilowatts, depending on you. Then, what is the energy equation considering a machine? What if there is a machine in a system? When a machine is a pump, the energy equation would be, what's the purpose of a pump? What's the purpose of installing a pump in a system? To add energy in the system. So it will add energy in the system. So the left side of the equation will have this term HA, or head added. So velocity head at 1, pressure head at 1, plus elevation head at 1, plus head added by that machine, which is a pump, equals velocity head at point 2, pressure head at point 2, elevation head point 2, plus the head lost. So I will show this later. So HA is called head added by the pump. So therefore, if a pump is installed, the power that it will generate is output power, Q gamma times head added. Why output? Because the input power to the pump is either electrical energy. For the pump to operate, you have to uh, plug it into an electrical source or driven by motor through fuels, so mechanical energy. That's why the output power is, when it is a pump, is Q gamma times head added, because the input is electrical or mechanical energy. So when it operates, that's the generated power is output power. So PO is power output of the pump. When a machine is a turbine, the input is coming from the water, if it's hydro or If the source is from the elevation of water, head of water, then the equation would be the head extracted by the turbine should be placed at the right side. So because the turbine will just extract energy coming from the normally the elevation head of water, such as in dams. You have to raise the level so that the powerhouse should be placed at low point farthest from the water surface in the dam so that the head will be high. So the energy equation would be when there is a turbine, velocity head at 1, pressure head at 1, plus elevation head at point 1 equals velocity head point 2, pressure head at point 2, elevation head at point 2 plus head extracted by the turbine plus the head loss in the system. So HE is called head extracted by the turbine. Therefore, for a turbine, it is input power because the energy comes from the head of water. If it is in the hydropower plant rather. So Q gamma times head extracted, where HE is called head extracted by the turbine. Then efficiency of machines, the efficiency therefore is 100% times power output over power input. Then energy grade line, EGL. So it is the line representing the elevation of the total head of flow. We call that energy grade line. The slope of the line is known as the energy gradient. The total energy at a section of the pipe with reference to a datum line is the sum of the elevation of the pipe center line, the piezometric height or pressure head, and the velocity head. That's the energy. And connecting those three forms of energy constitute the what we call energy grade line. The energy grade line will or slope down or drop in the direction of flow except where energy is added by mechanical devices such as pump. So the energy grade line will always slopes downward in the direction of flow. It will only rise when there is a pump machine that adds energy to the system. So take note the characteristics of an energy grade line. It always slopes downward in the direction of flow. The hydraulic grade line is the line joining liquid surfaces in a series of piezometers, imaginary piezometers. So in a closed channel, a line joining the elevations that water would reach under atmospheric pressure, as mentioned earlier, is called the hydraulic grade line. And the slope is called hydraulic gradient. So this is a line joining the liquid surfaces in a series of piezometers. The energy grade line and the hydraulic grade line differ by a distance equal to the velocity head v squared over 2g. If you can recall, the vertical distance between the energy grade line and the hydraulic grade line is the velocity head, with the energy grade line always above the hydraulic grade line. However, the two may coincide. The hydraulic grade line, the energy grade line is also the hydraulic grade line under no flow condition. So for example, in a tank, then there's no flow. It is just stagnant. The water surface, the liquid surface in the tank, which remains at the same elevation, is also the energy grade line and the hydraulic grade line. So they coincide. But in general, the energy grade line is above the hydraulic grade line by a distance velocity head. That's why when the velocity is zero, there's no flow, then this is zero. So that's why the energy grade line and the hydraulic grade line may coincide. So still on the properties of energy grade line and hydraulic grade line. So if this is the system, notice that the energy grade line is always sloping downward in the direction of flow unless there is a machine where it will rise. Then the distance between energy grade line and hydraulic grade line is always equal to the velocity head. So here it's v1 squared over 2g, which is small because the section at 1 is bigger, so the velocity is slower. At section 2, the velocity is higher, faster, because the section is smaller. So that's why the distance between the energy grade line and the hydraulic grade line will be higher velocity head. The two may maybe may coincide when there is no flow. The two will be parallel if the cross-section is constant also. Here they are not parallel because the cross-sectional area changes in the direction of flow. So to consider a system with a pump, we call this, if the flow is from left to right, this side of the pump is called the suction side. We expect low pressure or negative pressure, supposedly negative if this is just the source. But if there is energy initial, it may also be positive but low pressure only. So on the other side, if this is the suction side, then this is the discharge side where we expect high pressure or positive pressure. So the energy grade line always slopes downward in the direction of flow. It rises because of this pump here. Then from this point down, it again slopes downward. From this point down, it again slopes downward. So the drop in the energy grade line is the head loss due to friction of this pipe. Then it rises because there is a pump. The drop in this energy grade line here is due to the pipe friction of this second pipe on the discharge side. Then the hydraulic grade line. So this is, by the way, from discharge suction side to discharge side of the pump. This vertical distance, because it rises, is the head added by the pump. So in this case, V2 is greater than V1 because pipe 2 is smaller in section than pipe 1. So the hydraulic grade line will be closer to the energy grade line here because V1 is small, while at this section here, so they are parallel because the pipe is constant, but they are closer because V1 is smaller. For this section here at pipe 2, the energy grade line and the hydraulic grade line are parallel because of constant cross-sectional area at 2. However, they are farther because V2 is higher. So this is velocity head at 1, then this is the velocity head at 2, which is greater than that at 1. Then if this is the system, we have from bigger pipe, then we have this fitting here to connect it with the smaller pipe. Then the energy grade line always slopes in the direction of flow. The drop in the energy grade line from this point to that point is due to pipe friction, this vertical distance here. The drop in the energy grade line from this point of the fitting to that point is the head loss due to that fitting. And the drop in the energy grade line from this point to that point is the head loss due to pipe friction of this pipe. So that's the energy grade line. Again, the drop in this portion here is due to the head loss of that fitting. Then, because V1 is low, V1 is low in value, then it is closer to the energy grade line, and here it is farther from the energy grade line. So therefore, the property of the energy grade line, it always slopes downward in the direction of flow, unless otherwise there is a machine that adds energy to the system, while the hydraulic grade line may rise or fall depending on the change in velocity. So that's the first case. The hydraulic grade head also falls, but in this next condition here, we have from smaller pipe to bigger pipe. This is the energy grade line. It's the same. It always slopes in the direction of flow. And the drop in the energy grade line are already explained there. Then this is the hydraulic grade line. This time, it is farther at this portion of the pipe because V1 is higher, then here it rises so that it will come close to the energy grade line because V2 is low. So it should be close. So that's why the hydraulic grade line may rise or fall depending on the change in velocity. So that's the so let's have energy at a point. Now if this is the pipe and this is the end of the pipe, for this part it is exposed to the atmosphere. So at point A, call that point A, then we have point B at the end of the pipe which is exposed to the atmosphere. So at A, the only energy available at A would be its velocity head and pressure head. So energy elevation head is not there because remember the arbitrary or the datum is arbitrary. So if we consider point A, the datum should be through A. So there's no elevation head there when we talk about point A alone. Now at B, there's no pressure because it is exposed to the atmosphere. So this will be zero. So the energy at B will only be due to velocity head at B. Assuming the velocity at B is different or the cross-sectional area at A and at B are different. But if they are equal, then energy at B will also be velocity head at B or velocity head at A if V sub A equals V sub B. Kinetic energy flux, therefore, is actually power due to kinetic energy. So it is Q gamma times velocity head because energy flux is also power. So power is Q gamma times energy, the other hand.